Look at any major city skyline. What you're really looking at is a forest of steel. This incredible alloy is the invisible skeleton that makes modern architecture possible, allowing us to build higher, wider, and more complex structures than ever before. But why steel? What properties does it have that make it so indispensable? And how does a pile of rolled sections in a factory yard transform into the rigid frame of a billion-dollar skyscraper? In this video, we're going to trace the journey of steel from the mill to the monument. We'll explain the material science that gives it such phenomenal strength, break down the different types used in construction, and reveal the engineering secrets behind those bolted and welded connections that hold everything together. By the end, you'll understand exactly why steel remains the material of choice for spanning vast distances and reaching for the clouds. Let's start with the fundamental question: what makes steel so special? The answer lies in its mechanical properties, primarily its high strength-to-weight ratio and its ductility. Steel is incredibly strong in both tension and compression, unlike concrete, which is weak in tension. This means steel members can be relatively slender and lightweight while carrying enormous loads, but perhaps even more important is its ductility, its ability to undergo significant deformation or stretching before it fractures. This is a life-saving property in earthquakes. When seismic forces hit a building, a ductile steel frame will bend and absorb energy, allowing the structure to sway without collapsing. A brittle material would simply snap. Steel is also an isotropic material, meaning it has uniform properties in all directions, which makes its behavior highly predictable for engineers. This predictability is gold when you're designing a structure that must stand for a century. A pro tip for junior engineers is to always remember that while steel is strong, its weakness is buckling. A slender steel column can fail under a load well below its compressive strength if it is not properly braced against lateral deflection. Now, not all steel is the same. In construction, we use specific types for specific jobs. The most common is structural carbon steel, like A992 in the US or S355 in Europe. This is what you see in wide flange beams, columns, channels, and angles, the primary members of a building's frame. It has a good balance of strength, weldability, and cost. Then we have the steel you never see but is equally critical: rebar, or reinforcing steel. This is a carbon steel with deformations on the surface to create a better bond with concrete. Its sole purpose is to be embedded in concrete to handle the tensile stresses that the concrete itself cannot, creating the composite material we know as reinforced concrete. For more demanding applications, like bridges or high seismic zones, we might use high-strength low-alloy steel, which has small amounts of other elements like copper or vanadium to increase strength and corrosion resistance. A common drafting mistake is to specify a steel grade without considering its weldability or its availability, which can bring a project to a grinding halt. The magic of steel construction doesn't happen on the site, it happens in the fabrication shop. This is where the raw, mill-produced sections are transformed into the precise components of the building. Using detailed shop drawings derived from the structural engineer's design, fabricators cut, drill, and weld the steel. They create the connection plates, the bolt holes, and the complex assemblies that will be shipped to site. The efficient workflow secret here is the use of advanced software like Tekla or SDS, that not only creates the drawings but also generates CNC machine code, ensuring absolute precision. This design for manufacture and assembly approach is why steel construction is so fast. A pro tip is that the quality of the fabricated steel is only as good as the shop drawings. A single misplaced hole can mean a connection won't fit, causing massive delays during erection. Once the fabricated steel arrives on site, the ballet of erection begins. Cranes, often climbing with the building itself, lift the pieces into place. Iron workers, some of the most skilled tradespeople on any site, connect them. The connections are the heart of the structural frame. There are two main types: bolted connections and welded connections. Bolted connections are faster and are the most common for connecting beams to columns. High-strength bolts are tightened to a specific torque to create a powerful clamp force. For maximum rigidity, especially in the joints of a moment-resisting frame designed to resist earthquakes, we use welded connections. These create a monolithic Rigid joint but require highly skilled welders and strict quality control through non-destructive testing like ultrasonic or X-ray inspection. A common and catastrophic on-site mistake is to substitute a specified welded connection with a bolted one without engineering approval, as it completely changes the structural behavior of the frame. Of course, steel has its challenges, and two are paramount: fire resistance and corrosion. And like concrete, which is naturally fire-resistant, steel loses its strength rapidly when heated. At 1000 degrees Fahrenheit, it can lose up to half its strength. This is why all structural steel in buildings must be protected. The most common methods are spray-applied fireproofing, which is a cementitious or intumescent coating that insulates the steel, or fire-rated board enclosures. Corrosion is the other great enemy. To prevent rust, steel is protected by galvanization, a coating of zinc, or sophisticated multi-coat paint systems. The pro tip for corrosion protection is to pay special attention to details like end cuts and connections, where the protective coating can be damaged, creating a point of vulnerability. To summarize the key takeaways: 1. Steel's high strength-to-weight ratio and ductility make it ideal for tall and long-span structures. 2. We use different types, from structural carbon steel for frames to rebar for concrete reinforcement. 3. Precision fabrication off-site enables rapid, accurate erection on-site. And 4. Robust connections and proper protection against fire and corrosion are non-negotiable for a safe, durable steel structure. Now I want to hear from you. In the comments below, what's the most impressive or challenging steel structure you've ever worked on or studied? Was it a complex connection detail, massive long-span truss, or a tricky erection sequence? Your field experience is invaluable. If this deep dive into the world of structural steel has been valuable, please give this video a like and subscribe.